definitely put attention and definitely ask questions if you get stuck, because this stuff can get kind of tricky for someone that's not experienced. For me, like once you learn AVL trees, they're super easy though. Like it's interesting. That one, it has a difficulty curve, but once you learn them, you're good to go. So it's just for some reason people get confused when they first learn them. So let's try to get it through together. So okay, so last time, to kind of pick up where we left last time, we were just talking about binary search trees and how you're able to achieve potentially log of n access time if you're able to keep the height at a minimum, right? Because way back, like I'm talking like a week, 2 weeks ago or something, like if we scroll up, like it's rewind time, we did talk about those properties, right? And in the properties, we said that the maximum number of, no, not that one, maybe this one, yeah. In a binary tree with n nodes, the minimum possible height or minimum number of levels is the ceiling function of log base to n plus 1. Now that plus 1 is just a constant, so we can forget about it for now when we talk about big O. So it's really log n, right? So what this is really saying is that a tree that is really full, and that's something we saw in the video that was pre-recorded when I wasn't here, is that a complete tree or a full tree, something that's like really compressed up like this, if we can achieve a tree of that format, then we know for a fact, based on that property, that the height of the tree is going to be of log n plus 1, which is just log n. And because we know that, that means that if we can get to any node in the tree within log n comparisons, then we know that we can search through the tree in log n time, right? So we can search whether something is present in the tree or not. Furthermore, we can insert something in the tree in log n time, because again, we can find out where that spot to insert is, just like we would if something is present, and then throw it in there. So the trick is how we can keep the tree to be a complete tree, or in this case a balanced tree that actually achieves that log n height. And that's hard. That's like saying, okay, let's quicksort can be log n and log n as long as we pick the partition that's like right in the middle of the numbers, right? Well, yeah, but picking that, like actually the best case there requires us to look at the entire list of numbers, which if we did that every single time would degrade quicksort into an n squared time complexity, right? So the catch on quicksort of making it fast is picking good partition, which is a slow process if we're not careful. With trees, it's not that bad of a catch. With trees, with the AVL algorithm that I'm going to show you, you can actually achieve that balanced tree and not spend too much work on balancing the tree out. And you can achieve that log n speed for insertion, deletion, and access. So we have the trifecta or the Zelda symbol, right, for this, because we have access, insertion, and deletion, and all of them are log n time, which is amazing. Okay, so the trick is, to get this working, we have to find a way of inserting things into a binary search tree, but still keep the tree with the minimum height possible. So I did promise I would tell you some terminology last time, and that terminology was a degenerate tree. So just to make sure that I do cover that. When we're inserting numbers into a tree, we put the smaller numbers on the left and the bigger numbers on the right. So for example, here we could have the following tree, and we have 2 smaller than 4. We could also put duplicates here, because again, this is technically to the left of that 4. And so that is a binary search tree, right? Now, when I mention degenerate tree, what I am saying is a tree that basically just has one child throughout. So for example, if we insert a list of numbers that is actually already sorted, so like ascending order or descending order, you would actually form a degenerate tree, because if you insert 4, 5, 6, 7, 8, they're literally going to build this exact tree. Try it at home and you'll get the same thing. And so this is a degenerate tree, because it's basically like a linked list at this point. And the access time to find any number is going to be O of n time, right? So that's the worst case scenario. We want log n time. So what will we need to do for this to make it balanced? Well, we could do that by hand. We could start by kind of grabbing the middle and making that the root node, and then just throwing something on the left and the right of that, so like a 5 and a 7, and then maybe go ahead and throw a 4 and the 8 there. And while this is not the most perfect possible tree ever, because you could also have two things there. We have actually achieved that log n height in a way, because now at worst you have to look at this, and this to get to that 4, or the same to get to the 8. So that is only 3 comparisons when you have 7 numbers. Now that might seem like, oh, that's not a big gain because this is a small example, but it does turn out, as we saw by that property a couple of weeks ago, that this becomes log n access time. So of course, the trick is, how can we systematically have an algorithm that is going to convert something like this, or not even ever let it get to that level as we're building the tree, how we can keep things balanced so we can achieve something like this. And that is where the AVL magic comes in, okay? And yes, this is balance. And the balance concept is going to come from the idea of, like, imagine you're hanging, by a thread, this tree, and the tree is actually balanced, right? Because if you hang this with a little string up here, you can see how the whole thing tilts this way, right? Whereas here, when I'm holding it here, it's actually balanced, right? So yes, you can think of balance in that concept, and that will apply most of the time. Sometimes things don't look balanced, but they are, but that's really rare. So yes, you can go with that sort of mentality, and that'll be good to go. However, there is a proper definition for a balanced tree that I'm going to show you. Okay? So before I do that, I would like to copy and paste, because it's a really long name, of where AVL came from. Oh, snap. There we go. Paste. So it's 1962, so it's a pretty old algorithm before any of us, well, actually, no, some of us could have been born there, but I wasn't born at that point. And the two people that made it are these guys, Georgi Adelson-Velsky and Eugenio Landis. And if you notice, there's the A, there's the V, and there's the L, so AVL. Don't ask me why they chose to put 2 parts for that one, but that's what they did, okay? So that's an ABL tree, and let's talk about the actual definition of what it means for something to be balanced, because what they're doing with this algorithm is they're making the trees balanced, because a balanced tree guarantees that log n height. So balanced tree. So when you have a balanced tree, the way that you're going to check that is you're going to be looking at the distance from the root to a leaf, or to the next node actually, and then figuring out how far it goes from the root you're looking at. And the root, when I say root, doesn't have to be the actual overall root of the tree. It can, if you're looking at like a subtree. So for example, if I'm looking at this section, then I just consider this to be the root of that subtree. So when I say root, it's kind of just, it's not to be the root of the tree. And so what you're doing is you're basically measuring how far from that node you have to go to get to the leaf nodes. So for example, here, and this is where like it gets trippy, because remember like a couple of weeks ago when we were talking about height and levels, and we said that like height and level, they have different definitions of that. Like, you have a thing of what height 0 means versus height 1, and if that includes the root or not, and levels, and it was a complete like mess. There's no consistency in that, and this is gonna kind of feed off of into this. So let's kind of establish the rules first of what this is going to be. Okay, so I'm going to define height of 0 to be a leaf node. Okay, that is going to be considered height 0. And a node that is not a leaf node, but is away by 1 by a leaf node, I will consider that to be height of 1. So then this will be height of 2. This is height of 3. And then what are these? These are actually height of 0s, because again, they are leaf nodes. However, let's just say that this had a child right there. Then this would be height 0, and this will be height 1. Okay, so I'm just trying to establish consistency here of what I will consider height. Okay, so forget about the height in other cases. We're just going to talk about the height for this algorithm to be applied like this. Okay, it'll make the math a lot easier later on. Okay, so now that we know how to compute the height for every node in this tree, what we want to do is we're going to look at the sort of sub heights of each thing. So for example, right now I'm looking at the height of each node, and the way I'm computing the height is I am picking the largest distance between both children. Because if you think about it, the node here, this one right here, the real root node, I could actually split this height into two values. I could say the left height and the right height, okay? The left height is indeed height of 3 because, you know, you're going from 0 to 1 to 2 to 3, right? So you got 0, 1, 2 to 3. However, the right child does not really have a height of 3. There's only one node until it gets to the leaf. So I could say that this is really height of 1 on the right side, okay? Similarly, I can do that, for example, for this leaf node right here. Or sorry, not this leaf node, but this node right here, that's almost a leaf. This I have set as height as 1, but that's really because it's coming from this side. So really, this is more like the right side of height of 1, but here on the other side, it's kind of a leaf because there's nothing beneath it. So I'm going to consider this side to be height of 0. Okay? So what I'm trying to say with this is that I don't want you to consider height overall to be the biggest of both sides of the children, but I want you to have both a left and a right height. Okay? So let's just do like a mini test here, pop quiz and whatnot, and I'll ask you what the height of each tier is. Okay? So for example, we're going to consider this the left height, whatever's coming off on this side, and then the right side, whatever's coming on this side, and we're going to do that for all of them. So kind of overlay them like that, and let's number them. So we're going to say 1, 2, 3, 4, 5, 6, 7, 8. So think for a second what the answer to these are. All right, and then just blur them out in Twitch, what the height of each of those is. I'll start out by giving you 1 and 2. 1 and 2 both have heights of 0. And I'll do one more. Maybe I'll do 5. 5 is going to have a height of 2. Okay? So you do the rest. Just throw them out in chat. Don't all pick the easy ones with 7, and they. Oh, you're all doing them together. That's hard because now I gotta like do gotta line them up. But okay, so let's start with 6 is equal to 2. No, not quite. 6 is not equal to 2 because this only has a distance of 1. So I would argue that that's actually 6 is equal to 1. Close enough. Again, this is why we have to make sure we are on the same page with the height computations. And then the other, so the rest of you put them all in one go, but that's kind of hard. Let's look at. So you said 3 was 1. You are correct. 3 is indeed 1. You said 4 is 0, which is indeed correct. And then we have. Okay, that 2 looks weird. Let me rewrite it again so it looks easier to read. 2, 1, and then 7 and 8, you all said 0. So, yep. Okay. So you all have, for the most part, the right stuff. Good. So, as you can see, that so far, this is not rocket science yet. Okay? It's relatively straightforward how you compute those heights. So if I ask you now, write a function to compute the height of that node for the AVL algorithm, how would you do that? Well, you could be cheap and use a static variable, but I would discourage you from doing that kind of coding. I would still use recursion, but I would just go ahead and iterate all the way until I hit a null. So just like go all the way left until you hit a null. And then as you work your way back up the tree, you compute the heights, okay? So like, modify your traversal code, like I would do like the pre-order traversal, because that one just goes all the way deep before it gives back anything. And so, but actually, I mean, either any of the traversals could work too, though. But yeah, so in this case, you go all the way down, and then you keep track of how deep you're going by counting. So this goes like a 1, a 2, and a 3, and so on, right? And so when you hit this at the leaf node, then all the leaf nodes are always going to be 0 if there's nothing on the left, and then 0 if there's nothing on the right. But when you go back 1, then because you're adding, you're doing the math, then you can fill those in on the way back. So as you're unwinding the recursion, you can fill in all the heights. And so you're going to want to modify for the next assignment, you're going to want to modify basically your data structure for holding a node and add 2 fields, which are going to be left height and right height. And then you can just run your code to compute those or you compute them on the fly, and then use that for the algorithm. Of course, I haven't talked about the algorithm yet, but this is one of the pieces that you have to know how to measure, okay? So, now that we understand how to compute the sort of the sub heights of the left and the right children, let me go ahead and explain to you what a balanced tree is. A balanced tree is going to be a tree where every single node's heights, whether it's the left or the right, if the difference has to be less than or equal to 1. Okay? So let me actually write that down. This is really important. So if the difference between the height of the left and right subtree, so I'm talking about those left and right heights, is greater than 1, so in this I'm just going to flip it around. That way I don't have to say less than or equal to 1. Then the tree is balanced. Of course, if the height is oh wait. No. Not balanced, sorry. Forgot the word not there. Or not balanced. Okay? Not balanced. And then if the difference between the left and right, I should have just copied and pasted my other one. Subtree's height is less than or equal to, so what I was saying, less than or equal to 1, then the tree is balanced. Okay? The too long didn't read version of that is basically, if let's just call them LH for left height and right height. Okay? So if you take the absolute value of this, and that number is greater than 1, not balanced. Actually, if I want to be the fancy math, I think that I can write this like this. I think the vertical lines mean absolute value, if I recall my math days. Oh, no. That was fine if I had it. Yeah, I don't think that's correct math notation, but the point is that's easier to think about than that big blob of text. Okay, so basically, you take both heights and you subtract one from the other, and then if you want to make it life easy, just pick the bigger number and subtract it from the smaller one. But if you do it backwards, just take the absolute value of that. And the point is that if that subtraction gives you a number bigger than 1, then you're not balanced. And of course, you run this AVL tree magical algorithm to balance it. But if it is balanced, then you don't have to do anything. Okay? So basically, let's take a look at our example that we did. So let us see if the node here is balanced. Well, we said that the height of the left and the right are 0 each. So 0 minus 0 is just 0. That number is smaller than or equal to 1. So then that is considered balanced. We said that 3 and 4, the height was 1 and 0, right? So 1 minus 0 is equal to 1. Or 0 minus 1 is equal to negative 1, but you take the absolute value of that, you get 1 anyways. 1 is basically less than or equal to 1, so that means that you're still balanced. So it might look slightly unbalanced, but we still consider this to be balanced. Okay? Go further here. let's look at this node. This is of course balanced because we got 0, 0 again. But the more interesting one to look at is going to be this root node here. So we said that the height of this on this side was 2 and here was 1. 2 minus 1 is equal to 1, right? And if we did 1 minus 2, then that's equal to negative 1, but we take the absolute value of either of these and you still just get 1, right? So either way, 1 says that we're still balanced, right? Because it's only when we hit 2, right? So again, if we get less than or equal to 1, including 1 there, it's balanced. So technically speaking, this may not look balanced, but it's still considered balanced. The reason why we don't say, oh, okay, for that to be fully balanced, we have to make it like both heights be equal, because that actually would make it like perfectly balanced, as all things should be. But, you know, that's why I put the thanos there. But the reason why we have that slight flexibility is because otherwise the algorithm would not be log of n. It would slow it down. Okay? Did I flip them again? I might have flipped them. Yeah. Well, I actually no. I just forgot to write the word "not" there. But yeah, good call on that though. Okay. So yeah. All right. So I think you get it though. That's the important thing is to make sure you all get it. But yeah. So the reason why we have that flexibility of 1 is because sometimes it's impossible to actually get it balanced. Like for example, this tree right here that we're looking at, you can never get it balanced perfectly, right? Like, tell me what you could do. Like, unless you like chop this one of the pink nodes in half and like put it one half on the other side, then you're not going to get anywhere, right? So you have to give it some level of flexibility, and that's why we have that difference of 1 being okay. All right, and also it speeds up the algorithm. When you get to a difference of 2, that's when things don't get are not good to go. So how can we kind of show that? Well, let's go ahead and show some examples of not balanced trees. The simplest example is going to be this, right? If we compute the heights, we can see these are 0, 0. This is 0, 1, so we're still balanced there. But at the root level here, we can see that this is a height of 2 and this is a height of 0. That's not balanced, right? Because that number is bigger. 2 is greater than 1, you know, so therefore it is not good to go. Okay? Actually, I should just say 2 greater than 1. So yeah, okay? So that's not balanced. Another example of an unbalanced tree. I think that one. Let's try it out. So here we have 0, 0. Here we have 1, 0. These are 0, 0. Here's 2, 1. So that's still okay at this level. This is fine. And then this one's 0, 0. Notice this little notation I'm doing. I recommend you do this notation when you're doing the test. That way you don't have to write all the H's and whatnot. You just kind of put tiny little numbers on each side to signify you check the height. This is going to be 3, 1. That is unbalanced. Okay? So here, not balanced. Okay? Everything else is actually balanced except for that one node. So therefore, if even one single node is considered not balanced, then the tree entirely is not balanced. Okay? So, yeah. Here's one that's actually balanced but looks unbalanced. I think I can go hardcore and put one more there. 1, 2, 3, 4. No. I can't do that one. That one will make it unbalanced. Okay, like that. This does not look balanced at all. If you think about it, if I hang this with a string, as I said, this thing is gonna tilt. Like it's gonna tilt that way. But if you do the math, follow the science basically, then we can see that this is balanced. See that? Now here's something that I haven't said actually, but I should, and this might make it easier as to how I'm computing these numbers. When you're building these numbers, so for example, when I'm trying to decide what number to put here, what you're going to do is you're going to take the bigger of the two children numbers, okay? So for example, and then add +1 to that. So for example, here, you have a 0 and a 1. So you're going to pick the bigger one, so literally 1, and then you're going to add +1 to that, and that's how I'm getting the 2 here, okay? Now, when it's something like this, where they're equal, so 0, 0, then, you just pick one of them, whatever, and then add 1, which is how we get that, okay? Similarly here, we have a 1 and a 1, so we just pick any of them. So that's only sort of a decision you got to make when the numbers are different. So, like, again, this case here, okay? So pick the bigger of the two numbers and then use that. So that's an important point that I hadn't made, so make sure you all understand that. These are all things you would have discovered when you code this, because, that's why it's good when you code things, because you really understand how they work, because you don't think about all those little details until you're actually coding it, and you're like, oh yeah, that's right, I got to pick between them, and which one do I pick? You have to actually tell the computer, so it's good. It's how you learn these algorithms. That's why we make you code them, even though you don't code in the test. Okay, so I think at this point I have pretty much nailed down how to go ahead and compute the height of a tree and to decide whether it's balanced or not. The reason I'm doing this is because the AVL algorithm is going to balance the tree for you if it's not. So the way you're going to be basically running this algorithm is you have a list of numbers to insert. So for example, I am going to be inserting the numbers 1, 2, and 3. Okay? And I'm going to be inserting them using binary search, which means that, or not just binary search, but using a binary search tree, which means that if I have nothing in my tree right now, the first thing I'm going to do is I'm just going to put this as the root. And then the next number, I'm going to compare it against this, and if it's bigger, it's going to go on this side, or smaller this side. So it's bigger, so I put it here. However, every time that I insert a number, I'm going to check if my tree is balanced, okay? So when I insert the 1, I should in theory check. But right now, of course, we got a height of 0 for basically everything, because there's no children. So the tree is still balanced, okay? Once you check it's balanced, then you go ahead and you insert the next number. So now we got a 2, so 2 has to go to this side. So after we insert it, we have to update the height. So of course, every time you insert something new, it's going to have height 0, so you can hard code that in. But then you have to work your way back up to the root and update the heights. So in this case, this has to be updated to 1. Here's a little shortcut. You only have to update the heights on the side that you insert. So basically, I know there's nothing here right now, but even if there was this like massive tree, so like imagine that we had a tree like this. Just this massive tree. And you went ahead and you inserted a number that was like the biggest number you've seen, so therefore it would go here. The only heights you have to update are going to be what you inserted, this one, and then this one, but only the left one, or sorry, not left, the right one. You don't need to update anything here because it would not have changed because you haven't modified it, okay? So it's an optimization thing that you definitely need to put in, because otherwise, like, yeah, bad things, it'll slow down your code. And I mean, you're not gonna lose points if you don't do it, because that's what the write-up will ask you if you did it or not. But I wouldn't do that just because, like, oh, yeah, it's gonna slow it down. So yeah, so you only need to update the side where you're actually modifying it, okay? And when you're coding it, it's much easier to do it this way anyway. Okay? So next you have the 3. So it's still balanced, by the way, so we're gonna insert again. So the 3 is bigger than the 1, the 3 is bigger than the 2, so you throw it in here. So now you're gonna have 0, 0. You're gonna update this to a 1, and then you're gonna update this to a 2, and bam, you're gonna have that red flag that this is not balanced, okay? So, what do you do next? Next, you're gonna run rotations to balance it. And that's the AVL algorithm's primary part. Okay, so I know that we only have 20 minutes left, so obviously, we're gonna keep talking about this next week. But I am going to introduce you at least the rotations, if not at least half of them. Okay, so when you have a node that's unbalanced in this tree, the first thing you need to do is you need to identify it, as we have done here. And the next thing you need to do is you need to make what's known as a rotation. Now, how you decide which rotation you want to do is going to be based on which side of your tree is heavy. So in this case, the right side is heavy, right? So this is heavy, and this is not heavy. Okay, so we would consider this to be a right heavy tree. It's a right leaning tree or something, okay? So, what does logic tell us that we need to do? Well, logic tells us that if something is heavy on the right side, maybe we should shift some of that weight from the right side to the left side, because that side is not heavy, right? So like, you know, if I am carrying something like this, and it's heavy like this, you know, maybe I should shift the weight this way so it's balanced, right? So it balances out. So that's basically what you want to do, is you want to rotate things in this left direction to take things away from this heavy side. So in this case, what we want to do is what is actually known as a left rotation. Okay? We'll pause there, and now we'll talk about how these rotations work. So because it used to take me a long time to write these out, I actually wrote them at some point in the past, and now it's just easier to copy and paste them. So I'm going to just go ahead. I'm going to go ahead and paste them all four. But again, we may not get to talk about all four of them today. So the first thing I should sort of tell you is that even though you have four different rotations, they're all basically the same rotation in different ways. So if you truly understand how rotations work, which you should, then just knowing one of them is enough to be able to deduct the other three. So study smart, not hard. So learn how to do one rotation, and then just understand how to do the other ones based on the one you know. Or you could just memorize them all four. But let's be honest, 2 months from now, well, not maybe 2 months because you have the final, but like 3 months from now, you will not remember how to do this. So you know, let's be honest and just learn how to relearn later on if you need to. Okay? So let's talk about the first rotation. Now this looks obvious here, and it is. But at first, you know, when you first do it, it's going to be kind of trippy. So again, don't feel bad. We'll walk this slowly. It's going to be multi-day talking about AVLs, because it is one of the trickiest algorithms, especially coding it too. But here we have that left rotation that we need to do. So I went ahead and replaced the numbers with letters because I kind of want to abstract that idea of numbers and think of them more as variables. So, but we really have the same situation. We have 1, 2, and 3 like that. So what you see here is the before and after. So this is what we have. This is after we do the rotation. So this is, you really just got to think of this as strings hanging and moving things around. So, you know, maybe if I teach 302 ever again, I'll do some paper mache and put it with strings and then bring it to class and like rotate it. That'd be kind of cool. Like little crafting project, but that's assuming we ever teach. I said if we ever teach 302 in person again, considering how things are going. Okay, so yeah, here we have X, Y, Z, and after the rotation, you can see that we now have a tree with a different root. So whenever you do a rotation, what is going to always change is going to be the root, and depending on the rotation, it's going to be what can become the root. With this left rotation, as you can see, we kind of just bend this down like that, where we took the X and we kind of flipped it down, right? So just because I don't want to modify that example, and I do recommend that you take a screenshot of this and keep it with you during the test. Definitely, it'll help you out, I think, but you know, it's up to you. But yeah, what I'm doing here is I am just taking this and I'm sort of bending it down here. The problem with doing this is that I already, in the simplest version, so here, this is the simplest version. We don't have any of these children, right? So we just have these 3 nodes. So in the simplest of cases, we're really just kind of, I'll try to do this visually, but we're just kind of bringing it down like that, okay? That's what the rotation is doing. Of course, we may have a situation, so that's why we have this general case, where there's already children involved. And if there's children involved, there's going to be some readoption, to put it in an easy way. Okay, so there's whenever you do a left rotation or a right rotation or any of the rotations really, if you have all the children that you could have, which in this case is 4, you could have, you know, in this scenario, one of the children is going to get swapped who the parent is. And there's just no way around that. So that's the stuff that you have to kind of remember and keep track of, especially when you're coding. The reason why I hope is obvious here, because as we rotate this, there's already a children in spot 2. So you're like, okay, where am I going to put this children? Well, it's going to have to be adopted by X, and because it was already here, which means let's kind of analyze where that was. The 2 here is there because it must have been greater than X, right? Otherwise it would have gone here near the 1. So the 2 has to be greater than the X, but has to be smaller than the Y, because if it was bigger than the Y, then it would have gone on this side. Similarly, the 3 has to be greater than both X and Y, and also technically greater than 1 and 2, but that's obvious because they're children of X and Y. However, we know that it's less than Z. So if I ask you like in the test, like, okay, what is the range of numbers that 3 could be? Well, 3 could be any number bigger than Y, any letter bigger than Y, but it has to be less than Z. So I guess really only Z. It could only be another Z in here, I suppose, or unless there's like a Y sub 2 or something, right? And this has to be bigger than Z. So I don't know. Whatever they ask you after Z is could be there or something. I don't know. Whatever. But yeah, so because we know of those, we can make those deductions. Then we can assume that this 2, which we know is less than Y but greater than X, can just go ahead and go down here instead. Okay? So there's no need to memorize these things. You just have to understand them and kind of make sense out of them. That's how we get that. And that's literally what we have here. So yes, you could memorize the rotation, just remember where things go. But I think it's more important to understand it. So once you understand it, then you can just build it on the fly. Okay? So I went ahead and highlighted here in the cheat sheet what the child is that changes. The non-highlighted children are the ones that don't change. So only the highlighted ones are changing. You can see every rotation, there's going to be one child that changes. In the case of a double rotation, we won't talk about that today. So don't worry too much about that. Double rotation is basically just 2 of single rotations together. But they're done not on the same node. So that's all they are. Again, like I said, all the rotations are just the same thing. Because it turns out that the difference between the left and the right rotation is just mirroring the operation. So suppose that we are inserting the numbers 3, 2, 1. 3 goes there. 2 is going to go on the left side. We're still balanced right now. But when we put in 1, we're no longer balanced because of the root. Because the root's the one that's unbalanced, that means that we have to do the rotation on that. In this case, we have a left-heavy tree, so we want to make it balanced. So that means we have to rotate towards the right. So therefore, we have to do a right rotation. Again, it's literally going to be the same thing that we did for the left, just mirrored. So in this case, we just got to bring this down. Like that. And there you go. Now here's the important thing when you do rotations. And this is actually a good way to check if you like screwed something up. When the rotation is finished, all members of the tree should still be in the right order, like binary search order, okay? So like if you somehow end up with a rotation and like you end up with like the following 3, you're like, oh cool, it's balanced. Yeah, it's balanced, but it's broken because like how in the world did 3 end up here and 2 here when like that's impossible? Like 2 is smaller than 3, so it should never go on the right side, right? So, you know, red flag that that's a bad rotation because you ended up with things out of order, okay? So always, 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 your rotation should still maintain the integrity of the tree because that's the whole purpose we're doing this, right? We need to it's like, oh yeah, let me sort these numbers, but I'll lose like half the numbers in the process, like Stalin sort or something. You know, that's not going to help you out. So yeah, okay. So the other thing is these rotations are happening on the fly. So as you're inserting numbers, the moment you see something unbalanced, you balance it out and then you keep inserting things in there if you have more to insert. You don't just like try to throw everything in at once and then try to balance it out. It's possible to do that, but you're not going to get that log n speed that we want for like all three cases: insertion, deletion, and access, which is what we're looking for. It's a little bit different than something that we're going to learn later, which is called heaps, where with a heap, you can actually throw everything in and then heapify it, which does magic to the tree, and then you're good to go. But then again, heap sort is still n log n, so not good for our cases. Good for sorting, but not for our cases. Okay, so let's just kind of review the general case for the right rotation since I showed you what it's like. So again, it's literally the mirror version of this. It's like if you hold it in the mirror, that's what you get. So here we have x, y, z, and again, don't actually no, the letters are actually alphabetical here, but don't think about the letters too much here. Okay, we have the numbers 1, 2, 3, and 4, which just represent some nodes. We're not saying that the number is actually the number inserted here, because you know, otherwise, like I said, here it's okay, they actually work out, but that's not my intention. But yeah, when you do the rotation, again, one of the children is going to be changed. It's going to be basically adopted by the. It's like if we have a kid, a kid, a parent, and a grandparent. Okay, and like basically after the rotation, the grandparent is going to take one of the grandkids and adopt it, because the parent is like doing stuff. Okay, it's kind of weird, but you can think of it that way if it helps. But here, let's just kind of do it here by hand. So what's going to happen is we are going to take this and we want to balance it, so we're going to bring it down to where this is, but of course that's already there. So we're going to pull that out for a minute. We're going to put in the z in there, but now we got to put this in. But again, this was after the y, but we know because of the way it was the tree was originally that it was on the left of z, so it's smaller than z, but it's greater than the y. Therefore, greater than the y is on this side, smaller than z is on this side, so it's going to go in the one available spot. Okay? So yes, they want to buy a lottery ticket or went to the gas station. So yes, okay, very sad, but yeah. So that's going to be again your other single rotation, and together between the left and right basically cover all of those cases, because I mean it's either left heavy or right heavy. There's no like middle heavy, because that would be balanced, right? So yeah, we got 5 more minutes, so I'm just going to do some examples, some practical examples that are not going to have double rotations in them. So again, if you start out coding this, you are going to run into a situation where the double rotations will be needed, but we'll cover those next week. So let's just insert some numbers. So again, let's just insert 1, 2, 3. That of course is going to rotate. So we're going to bring that down. Okay, let's insert another number. So let's say we have a 4 after this. So where's the 4 going to go? Well, the 4 has to go here, but we got to check if everything's still balanced. So it turns out that it is balanced. Very good. Let's just say we have another 3 that we got to insert. Well, that second 3 is going to go bigger than 2, but small, but you know, equal to 3. So it would go there technically, because we said that duplicates go to the left side. And so that's still balanced. We just update this to a 1. We don't need to update the 2 because this 1 was already the biggest one before, and now it's just equal. So we can, you know, it's an optimization that you don't need to change this, just like none of this has to change right now. Okay, let's go ahead and insert a, let's insert a 0 in there and see what happens. Okay, so we insert a 0, that's going to go there. 0, 0, 1, 0, 2, 2. So it's still balanced. let's insert a -1 since we ran out of numbers. -1 is going to go here. That is no longer balanced because, as you see, when you compute the heights, this is a 2. So then you can perform it's left heavy, so you're going to rotate to the right. So right rotation. So in this case, this is going to come up, and the 1 is going to go here. And as you can see, a good way to verify if the rotations are going okay is that the tree still like actually binary search, which it is. Okay. Let's go ahead and insert another number. So let's go ahead and throw in a -2. In this case, we have 1, 0, we have 2, 1, we have 3, 2, so it's still balanced. Let's go in and throw in a let's throw in a 0. Okay, 0 there. So now we have 0, 0, and then this becomes 1, 1. This becomes a 2, 1. These are 0, 0, and that's 3, 2. So everything is still the same. But now let's throw in a -3. Okay, this is where things get fun. So 0, 0. 1, 0, 2, 1. We pick the biggest of the two numbers to bring up, which is a 2, so that becomes a 3 up here, and that's unbalanced. This was more interesting because there's children involved. Now, just to not get confused with all the little numbers here, I'm going to erase them. But that is technically unbalanced, right? At this level, because we have 3, 1. Because this one's okay because it's a 2, 1, right? 0, 1, 2. So that's still okay. So the unbalancing situation is happening here. Okay, so this one, you know, it looks bigger now because there's children involved. So it might look intimidating, but think back to the algorithm. Yeah, 2 minutes left. So in this case, you know, I'll color code it. These 3 are going to be these 3. And then the blue children is going to be that. Oh, that's not blue. Well, here, let's just color code these 2. That would be this and the non-existing one there, so we don't have to worry about that one. And then the actual blue is this one. And then let's just color code this to be that. So once you color code it, it's kind of just obvious at that point if you know the algorithm there, where things are going to go. But you know, even if you don't, you can just kind of do it on the fly. So this here is going to eventually move down to here, like that. And then the 0 here, which was the child before, is going to get readopted, right, by the grandparent, right? Because of the milk. Blame the milk. So like that. And there you go. You just reconnect it with the new root, which is that. So let's bring that up so it looks more nicer. And did it work? So after you do a rotation, the first thing you should do is check whether things are balanced now. As we will learn next class, that they may not be balanced with a single rotation. But in this case, they are, because I said I was going to do examples that are actually only requiring 1 rotation. Okay? So the time is up. So I'm going to leave you with a scary set of numbers to insert, and then I'll let you see if you can rotate them. So I want you to insert 1, 3, 2. So 1, 3, 2. As we can see, this is not balanced. So just those 3 numbers are not balanced. I want you to try at home to do a single rotation on that and see if you end up with a balanced tree. And if you don't, spoiler alert, it's not really going to work. That's going to be an example that's going to require a double rotation. So that's what we'll pick up and show you next class. All right, so we're halfway there with the algorithm. So hopefully you're feeling comfortable. But if not, again, like I said, we're going to spend the next class entirely just doing double rotations and then just showing you full examples and whatnot. So I think by the end of this, you should be really strong with the AVL algorithm so that you can have your perfectly balanced trees. All right? So let me know if anybody gets stuck on the homework and everything. But, you know, remember 6 and 7 are due back to back because they are basically the same assignment, just split for grading purposes. So, yes. And stay tuned to the Canvas announcements so that I can release the link to the, I'll do that tonight probably. So I'll release a link to the survey so that if you want to start going tomorrow, you can. I encourage you to do it as early as possible, but, you know, not like desperate to get the information going. But definitely check if the app is available. Because if you have problems downloading the app, that's something that we have to update on our end. Okay? So I will see you all later. There's a lot of assignments ahead, so make sure you all remain calm and get everything done in time. Okay? So see you guys later.